Welcome. Today we want to discuss about maximum and minimum values of functions of two variable. I would like to start with the quote of Jean-Pierre. So Jean-Pierre is the greatest mathematician still alive. He he was the youngest Fields medalist of his time. Okay. So the quote says, alas, most people are afraid to admit that they do not know the answer to some question. And as a consequence, they refrain from mentioning the question, even if it is a very natural one. What a pity. As for myself, I enjoy saying, I don't know. So we want to start with function of many variables, and we want to talk about local maximum, local minimum, and global maximum, global minimum. So what is local maximum of a function is? So consider the function of two variables. So you see this peak here. This is a local maximum. Now, if you recall for function of one variable, you had local maximum here when you can get a small interval around this point, let's say this point A, such that f of A is greater than or equal to f of x for all x in some interval, some open interval containing A. So similar to the story here. So consider a function of two variables, f of x, y. It has local maximum at point A, B. Say, for example, here, let's consider that point to be P. It has local maximum at P if there is a disk. So disk is like a circle filled inside, but the boundaries are not there. So it's in a disk. On this disk, inside this disk, your f value is greater than or equal to all the values of the function. So it means that f of xy is less than or equal to f of ab for all xy in this disk. Yeah. So I'm writing disk p at around p of radius r. This r is unknown to us. So this gives us local maximum. Similarly, what is local minimum? So local minimum at AB, so a function has local minimum at AB, like here, if, again, at this point, P, I can draw a small disk containing P, an open disk of certain radius, such that this value at P is the smallest one. That means f of AB is less than or equal to f of xy for all xy in this disk. Then we call f of AB as local minimum value, and in the earlier case, f of AB was the local maximum value. Now comes the concept of absolute maximum and absolute minimum. So what is absolute maximum? Also called as just maximum or global maximum. So it is the largest value of function on the domain, right? So here you see that this point is also local maximum and global maximum. So what is an absolute maximum? Absolute maximum of a function is at point AB if f of AB is bigger than all f of x, y, where xy comes from the domain of f. And similarly, we can define absolute minimum. So question is, if I give you a function, how do we decide whether the function has local maximum or local minimum? So for that, we have Fermat's theorem. So Fermat's theorem says the following. Suppose you have f has local maximum or local minimum at AB. And on top of that, the first partial derivatives of f exist there. Then fx at AB should be 0, fy at AB should be 0. That means both the partial derivatives should become 0 at that point. Here is an example. So as you see, so here, if you look at the partial derivative, so this is along the direction of y because x is fixed, right? So x is some fixed value, right? So along here, the partial derivative at this point, so let this point be AB here, AB, we see that partial derivative at AB is 0. Why? Because it partial derivative of f with respect to x at AB represents the slope of this line, and this line is horizontal, right? So therefore the slope is 0. Similarly, we will see that partial derivative of with respect to y of f at AB, which is along this point here, is also 0. So this is what Fermat's theorem is. So a critical point of a function is f is such that the partial derivatives, both partial derivatives are 0, or one of them or both of them do not exist at that point. Okay, so right. So now the big question is, how do we decide if the critical point is local maxima or local minima? So we want to classify these points, right? Because it seems that if you have local maxima or local minima, that they correspond to critical point. So is there a mechanism of having a critical point and then deciding if they are local maximum or local minimum? So for that, we have what is called a second derivative test. So let AB be a critical point of xy, f of xy, and let f have continuous first and second order partial derivatives in some circular disk containing AB. Then you define d of AB, which is fxx AB, fyy AB minus fxy AB, the whole square. This is called discriminant or Hessian. So you can also see this as actually as fx xab, fxyab, fxyab, fyyab. So you can see this also as a determinant of this 2 by 2 matrix. So based on this discriminant and the sign of the first of the fxx of AB, we can decide whether the critical point is local maxima or local minima. So this is a test. So if this discriminant at AB is greater than 0, so here when I write D, I mean D of AB. So if D of AB is greater than 0 and fxx AB is greater than 0, then f has local maximum at AB. Similarly, if D is greater than 0, then fxx and fxxab is less than 0, then f has local minimum at AB. And if D is less than 0, then you don't need to check anything. It has neither local maxima or no local minima. It becomes instead what is called a saddle point. And if D equals to 0, the test fails. So the second order derivative here, you see the discriminant consists of the second order derivative, and fxx, which is dou square f by dou x square at AB. So the sign decides whether the point is going to be local maxima, local minima, or saddle point. So what is the saddle point? If you recall the thing which goes on the top of a horse is called saddle. So the way saddle looks like is the following. So this point here is the saddle point. Let me make it slightly more dramatic so that it's clearer. So this point here is the saddle point. Now note that it is neither local maxima nor local minima. So if you see along this curve, it is maximum. If you see along this curve, it is local minimum. A better picture is in this here. So you see that 0, 0 here is the saddle point, because along this curve, it is minimum. Along this curve, it is maximum. So you see that in this case, if you look at this curve here, that in that case, x is fixed and y is changing. So at this point, we are looking at the slope of the line, tangent line to this curve here. This will give me that dou f by dou y at this point, which is 0, 0 is 0. And along this curve, if I draw that, I get that is also horizontal. So both of these are horizontal. So we get 0, 0 is 0. So we get the critical point. So the classification of critical point is it's either local maximum or local minimum, or it's a saddle point. However, when D is 0, the test fails. So if I want to write it as a tree, this is what I'll do. First, I will check for D, and then I'll see the cases. I'll see for the case D less than 0, D greater than 0, D equals to 0. And if D is less than 0, then it's a saddle point right away. However, if D is greater than 0, then I will again check for fxx. So we are checking at a point AB. So if fxx is less than 0, if this is less than 0, I get local maximum. And if D is, if fxx is, if fxx is at AB is greater than 0, then we have local min. And if D equals to 0, then the test fails. Test fails. Need to apply some other tests or methods. Okay, still you can do some classification there, but so now note that critical point is a point at which the derivative is both the partial derivatives are either 0 or 1 or both of them do not exist. Okay, so let's look at the following problem. So find and classify the critical points of this function fxy x cubed minus 3x plus 3xy squared. So before I go to do the classification, if you plot this on Wolfram alpha, if you ask for stationary points of this, it will tell you that you have stationary point at -1, 0, which is maximum. And at 1, 0, you get minimum. So you see this is a maximum value, whereas the other one is a minimum value. And it also tells you that there are saddle points. So the saddle points, if you ask saddle point of this function on this range, it basically gives you the one of the saddle points. Okay, so you see here along here it seems to be, and then you have maximum along that curve. So let's investigate this now. So let's try to find it now using algebra or computation. So first step is to find out. So step 1, find critical numbers or find critical points. In this case, it's critical points. So critical points. So we need to find critical points. So for that, what we are going to do is we are going to differentiate with respect to x, and then we are going to differentiate it with respect to y, and equate it to 0 and work it out. So in this case, we have partial derivative with respect to x is going to be, or I will use the other notation fx as well, is 3x square minus 3 plus 3y square. And then I get fy is the first two part will be 0. I get 6xy. So now I need to solve this together. So fx equals to 0 equals to fy. So let's see. So easy way would be to look at fy. Fy equals to 0 implies x equals to 0 or y equals to 0. So now if x equals to 0, substitute in, so let's give this equation names. Sub x equals to 0 in 1, we get 3y square minus 3 equals to 0. This gives me 1 equals to y square, which gives me y equals to plus or minus 1. So therefore, the points are, we got 0, 1 and 0, minus 1. So these are two critical points we got out of taking x equals to 0 here. Now let's consider the case if y equals to 0. This will give me 3x squared. So sub this in 1. So substituting y equals to 0, sub in equation 1, we get what? We get 3x squared minus 3 equals to 0, which will give us x equals to plus or minus 1. So therefore, we get what? 0, minus 1, 0, and we get 1, 0. So now we have here, let's make a table now. So we got critical points. So we got this critical point. So we want to employ now the second derivative test. So let's see. So what do we need to compute for the second derivative test? We need to be able to compute this d, which is the discriminant. So let's first compute d now. So what is d? So d is fxx. So let's say d of d of xy. Just to make it clear, it's a function of x and y. So fxx fyy minus fxy square. So fxx is the derivative of fx with respect to x. So derivative of this with respect to x is going to be 6x. So we get 6x. Similarly, derivative of this with respect to x is also, so derivative of this with respect to x, sorry, fyy is going to be again 6x minus fxy or fyx. So if we take this guy and take derivative of this with respect to x, we get 6y. So this is our d. So and then this square, so this is going to be 36 x squared minus y squared. It's a good idea to simplify this. So now we want to classify the critical points. So I'll make this table here. So let's put the points in. So let's have this table. So we will write down critical points. We'll write down D at critical points. So critical points A, B. We'll write d of AB. Then we'll compute fxx, which is going to be, what fxx is 6x, and then we will have our conclusion. Okay, okay. So first point, so we have got 4 points. So let's look at the first point, which is, so let me write down all the points here. We have, these are our critical points. So we got 0. So let's write it down. We have 0, 1, 0, -1. Then we have -1, 0, and then we have 1, 0. So now D is 36x square minus y square. So let's put the first one. So 36x squared, 0 square minus 1 square. So this is going to be minus 36, which is less than 0. Same way here, minus 36 less than 0. In this case, we'll get 36 times x squared, which is 1. So which is 36 greater than 0. 36 greater than 0. So in this case, we don't need to do this computation. The conclusion right away is saddle point. So 0, 1 is a saddle point. Similarly, 0 minus 1 is also saddle point because we got D to be negative. Now, if D is greater than 0, then we have to do the next classification. What is fxx at 6? At 1 minus 1, 0. So we have to substitute the x value here. We get -6, which is less than 0. And here we get +6, which is greater than 0. So in this case, we get local maximum and we get local minimum. So quite an interesting example. All the 3 things show up in this example. So this is how we find and classify the critical points. All right, so let's look at an application of this thing. So suppose we have a cardboard without a lid to have a volume. So cardboard box without a lid to have a volume of 32,000 centimeter cube. Find the dimension that will minimize the amount of cardboard used. So now if you look at this problem, first of all, let's draw a cardboard without a lid. So cardboard box without a lid looks like this. So the lid is not there on the top. Now, one of these sides is, let's have this side to be X, this side to be Y, and this side to be Z. So Z is the height. So what are we given? We're given X, Y, Z is equal to your volume, which is 32,000, which is your V. Now we want to minimize the amount of cardboard used. So this cardboard is used to make the surface area, right? So cardboard is used to make surface area. So what is the surface area of this cardboard? So surface area of this cardboard is, so we have XY for the bottom surface area and so YZ for the other side. So it's 2 times YZ for this side here. So 1 YZ for this part, another YZ for this part. So 2 YZ, and then we have xz. So we have xz1, xz for this part here, and the other is xz for the part behind. So we have plus 2 xz, and this is our function which we want to maximize the surface. However, it's now become a function of three variables, and we want function of two variables here, right? So our theory we have developed here is for function of two variables. So interesting question would be, can it be extended to function of three variables? And the answer is yes, you can, but D will look different. So we'll not go into that. So from here we get, what we get is Z equals to over XY. So we'll sub it in here. So we get XY plus 2 times YZ. So YZ, so Z can be written as, so we get 3200, so 2y divided by xy plus 2x divided by 32000 xy. So we get, this implies this is same as xy plus 64000 times x 1 by x plus 1 by y. Okay, so this is my function which I want to minimize. So let's call this as SY, so surface area. So first step 1, find critical numbers. Or we should call it critical points. Okay, critical numbers are the terms used in function of one variable, right? In function of two or more variables, usually this critical point. Now note here that x and y are both greater than 0, right? One may say, well, why can't x and y be 0? Well, if they are 0, then the volume cannot be 32,000, right? So first step is to find critical points. So for that, we'll take partial derivative of this with respect to x. I will use the Sx because it's more compact. That's the only reason why. Sx equals to, so first of all, what is Sx? Sx is going to be y plus 64,000 multiplied by minus 1 by x squared. And I get Sy equals to x plus 64,000 times minus 1 by y squared. So now we'll sub one into the other. So first of all, let's say Sx equals to 0 implies y equals to 64,000 divided by x squared. So let's call this equation 1. Equation 1, equation 2. So sub in equation 2, this will give me what? This will give me that if I sub this in equation 2, I will get, so we got, so I'll get, so here we get x equals to 64000 divided by y square. So y square is going to be 64000, the whole divided by x square, the whole square. So when we multiply it on the other side, we get we'll get x cube equals to 64000, which gives me x equals to 40, right? So 4 cube is 64 and there are 3 zeros. And when I substitute sub in equation, if we substitute it here, we get y equals to 64000 divided by 40 square. That will give me 40x ball. So I got the only critical point we got is 4040. Now we need to see if it maximizes or minimizes this, right? So it could happen that, or it's a saddle point. It doesn't either. So for that, we need to investigate the second derivative. So let's compute sxx is going to be derivative of the first equation with respect to x. So that's going to be 64. So 2 times. So 12800 divided by x cubed. Syy, again, so equation is so symmetric that you will get 12800 divided by y cube. Now sxy, take this guy and take derivative of that with respect to y, we get 1. So d is going to be at xy is going to be 12800 square x cube y cube minus 1. So now let's see. So we have only one critical point, so I'm not going to make a table. So let's d of 40, 40. So d of 40, 40 is 12800 square divided by 40 cube times 40 cube. Now 40 cube is 160. So we have, well, sorry, 64,000. So we have 12800 square, oh, minus 1. So 64, the whole square. And you can see that this is going to be clearly greater than 0, right? Because the top is the 4 times of the bottom. So this is greater than 0 because all we need is a sign. So therefore we can classify it now, right? And we have sxx at 4040 is clearly 12800 divided by x cubed, which is 64,000. That is 2, which is also greater than 0. Therefore, what 4040 is a local minimum of S of xy, and hence we get x equals to 40 and y equals to 40 minimize the surface area. So that solves this problem, right? So now, so we'll do some more problems in the class, and we are also interested in absolute maximum and absolute minimum. That is the next part of the discussion. Thank you for your attention.